Okay, so it's noon sharp, and that was the hour when we have foreseen to start this ASHVIN webinar session. So I propose that we start right away to be able to use this hour as efficiently as possible. So welcome everybody. My name is Mona Maril, and I am the communication and dissemination leader in the ASHVIN project. And today I have a great board of 4 speakers with me, speaking about digital twin technologies and how we in ASHVIN project have developed and validated those technologies for the maintenance of civil engineered assets. So we are really pleased to see you numerous today with us, and we are really happy to share the research results from our different demonstration sites. Just before we start, some housekeeping issues. This session is recorded so that everybody can watch it again through our YouTube channel. If you have questions to our speakers, I would propose you to keep them until the last 10 minutes of the session, where we will have an interactive part where you can ask and our speakers can explain a bit more the points that were maybe unclear to you. And finally, let me just share my screen so that we can quickly run through today's agenda, and then I will give the floor to our speakers. So today we will start with a short introduction to the ASHVIN project. Our technical coordinator, Rahul Tomar, will explain you what ASHVIN is and what are the challenges that we try to solve with this research and innovation project. Then we will have a better look into the maintenance of infrastructure assets that we are also working on in the project, and we will give you an insight to the different tools that we have developed for this purpose in the program. And then we will have 3 different use cases that we will discover where we have actually deployed the ASHVIN technologies in the field across different civil engineered assets in Europe. And then, as I promised, at the end, we will have the more interactive part where we hope that you can ask your questions or exchange ideas or challenges that you have faced related to the topic. So we would conclude the session with that. So with this, I would pass the floor to Rahul Tomar from Digital Twin Technologies in Germany, who is the technical coordinator of the project. Thank you, Rahul, and please go ahead.
Thank you, Mona. So good morning, everyone. My name is Rahul Tomar. I'm presenting here, giving you the overview of the ASHVIN project. So ASHVIN project, this is Horizon 2020 funded project for the span of 3 years, which has been started in September 2020. So 2020, yes, that has been started that time. So this project, we are having 14 partners from all over Europe, which it's a 3 years research project, about 5.6 million of Europe complete budget. We have partners from north to south of Europe to take the span of different condition of the construction site, different environment of the construction site to understand and to validate the project. So that was the basic reason to start from all part of the Europe to take the demonstration sites. What ASHVIN, so the ASHVIN project is about not only about the construction only for one phase when the construction is happening. It's a whole 3 span. So design part of infrastructure, construction part of the infrastructure, and monitoring part of the infrastructure. In this project, we are not developing anything from the scratch. We are not reinventing any wheel. The most important part for us, there are many things already there in all the 3 phases, to connect these things into one platform so that seamlessly the data can flow from design till the monitoring of the infrastructure and into one platform. Into one platform does not mean the platform has to be from the ASHVIN, for example. ASHVIN is creating the tool that can be integrated to other software tools also, so that it can be easily taken care within the different industrial sector, different industry partners to go for and validate those tools. We have seen in our previous, this is our second technical webinar. We have done the technical webinar previously about the construction phase, that what are the tools we have developed. And this specific webinar is very much focusing on the monitoring of the infrastructure. These are the tools. So we have 10, 11 tools which has been developed during the project. Yes, this time those tools has been developed with different knowledge from the research partners and industry partners among different phases of the infrastructure for taking the KPIs. So KPIs that every industry is looking for is about better scheduling forecast, better allocation of the resources, reduce number of accidents, and reduction of cost by 20%. So this is one chart, one figure which we are showing how the tools are connected to specific KPIs and to accept those things. So when we are talking about reduction of cost by 20%, it is going to be like this, which we are going to prove in the end of the project deliverable also, that how industries, construction company can reduce their cost using those digital tools. This is the workflow, the data flow, basically, how the data is to be collected and then go up, consumed by those tools and provide the result to the construction manager. I'm not going to explain the complete this workflow at the moment. It will be presented it will be provided as other tool also. So I would like let other tools to be presented in next time for this. The the basis of the whole ASHVIN platform is about the IoT platform. Because for any to make the construction site as a digital the first point is to have all data on digital form. Data on digital form does not mean that in different places, has to be on a single places. That's why the IoT platform makes very important role in the whole ASHVIN tool project, that the data to be collected from different data sources, saved in a specific one single central source, and then can be consumed by different tools which has been developed by the tool developers here, and can be utilized by the construction companies to see their KPIs or to increase their productivity for that case. So in the bottom, you can see that all the different sources, the IoT platform which has been used in this ASHVIN platform, ASHVIN project, is from via Mainflux, one of a partner from Serbia. This platform is device agnostic. You can take any sensors, any device to be connected on this platform. Doesn't matter which protocol you would like to consume. It can be connected, and it is very standardized by industry, even used by the Intel in many projects of theirs. And then from there, you can use multiple. You can create your own dashboard, or you can use the dashboard which has been provided by the ASHVIN to see the result. So this is a very quick overview I have given here about the ASHVIN, and I will let my colleagues to present further from the monitoring phase. Thank you.
Great. Thank you, Rahul. So next, we will have Rolando Chacon from the Polytechnical University of Catalonia, presenting us a more focused work on the maintenance of the infrastructure assets within the ASHVIN. So Rolando, please go ahead. The floor is yours.
Thank you very much, Mona. And thanks for all participants being here with us. So today I would like to present these ideas and these developments on digital twin applications for maintenance phase. Okay? And this specific presentation is addressed to designers, operation managers, infrastructure managers. Since designers are faced to simulations, predictions, analysis, operation managers are faced with data collection, visual inspections, assessment, and infrastructure managers are faced with maintenance plans, asset management, networks, and even procurement. So with that said, the stakeholders that can help assist in this maintenance process. Okay, that's the question, and that is the development behind this webinar. And this project. This digital twin, which is an interface, if we see interfaces, sizes and complexities of these interfaces in time, at the beginning, we had, of course, physical archives with all information from the assets, or even siloed digital archives that became interconnected with the web. And more recently, some years ago, BIM has been in the market in construction industry, in which assets are digitized in a way that are not only geometrical information of the asset, but also metadata of the asset is encompassed. And now if we go a little bit further, we see this digital twin as an extension of the BIM, in which we may argue in which stage we are so far. We are like approaching the first generation of comprehensive digital twins, or are we still like in early ages? But in any case, this first generation of digital twins should encompass many types of information together, okay, many pieces. And so this virtual representation of the asset that encompasses not only maintenance, but the prequel of design, the construction phase, and even after the demolishment, this virtual representation encompasses also many different domains, maybe structural domain, maybe architectural domain, management domain, mechanics, electricity, plumbing, many types of information together, and also many types of data together, and synthetic data, such as the geometrical representation, data related to the products, data related to processes, and from simulation. And so how can we make that this virtual representation is useful for designers, operation managers, infrastructure managers alike to plan maintenance safely, efficiently, productively, and economically sound? Because that's a big goal. And for that goal, then what one single virtual representation may be even aggregated in forms, in networks, or even cities in which they belong, and they can communicate between virtual representations. So that's a very, very big goal for digital twin vision. But that challenge is quite big. We have three axes here. I will present this idealization of three axes, in which one axis represents the phase, design, construction, or maintenance. One axis represents the domain of information, structures, mechanics, architecture, management. And the other axis represents the scale, city, network, asset, or a single element of that asset. So it's a very complex many legs of information together to create this virtual representation. That's a big challenge. So to tackle this challenge in this project, we have had the opportunity of working with 10 different demo cases, demo sites, covering design, construction, and maintenance, covering different types of information and nature of those assets. But today we will focus on those related to maintenance, okay, which are bridges, stadium roof, and an airport in Croatia. Okay, specifically demo 1, demo 7, and demo 3 we will discuss today. And to present it systematically, I put here 4, let's say, steps, which are all related to data collection, different techniques, simulations and predictions, different domains, risk assessment, different KPIs and stakeholders, and also this spatial integration with the different scales we can have. Again, I insist, the idea is to provide this assist to assist to the generation of data-informed maintenance plans. Okay, so the coexistence of measurement, simulation, assessment together in a geographical system, information system, is a big challenge. Okay, this coexistence, it implies that the informatics help all this type of information being together. Okay, so for that we use an approach of a knowledge graph. Okay, this knowledge graph is an let's say I'm talking now technically in programming quotes. in which one single asset with many different type of data sources and multiple interconnections between those data sources can be tackled together. Okay? Here we see circles that represent sources of information, and these sources of information can relate to other sources of information separately or jointly. So this is called knowledge graph. I really invite you to have a little look on this term in your search engines to see what it may represent. So when it comes to this step, let's say data collection, we have had many multiple sources of information. Okay, in particular, sources of information that are time streams coming from sensors giving information, structured information. Okay, that is retrieved and then sent to the IoT platform. But we have also worked with other techniques like remote sensing techniques, let's say point clouds, which is unstructured information, or images, that is also unstructured information, more abstract ways. But all of those sources of information belong to these demo cases we have been working with. Okay. On the other hand, simulations and predictions, multiple domains, and here I present this name ASHVIN, which is one of the enablers to link these simulations with the digital twin. Okay, let's say for one demo, which is belongs to the bridges domain, we have developed this connection between the numerical methods to predict nonlinear, let's say, failure of the structure of the material. So the question here has been, can we embed validated simulations able to predict material or structure failures, okay, within this digital twin? Another question and another approach has been with numerical methods. Can we develop realistic simulations based on the actual seasonal shapes of the assets, if we are talking about continuous monitoring? Okay, in this case, ASHVIN has helped to enable this analysis using commercial software. Other more in-house built software in which we had to develop very complex numerical simulation of roof stadiums. But for that, we needed to also embed into the platform computational retractable models, okay, to understand in a simpler way, okay, this complex behavior of such assets. And also predictions that are not necessarily based on simulations in physics, but also in data-driven techniques, okay? So that has also been part of this way of connecting prediction and simulation to the digital twin platform. Third step is the risk assessment, in which we have this tool called RISA, okay, which systematically using information from the end user, we can develop this type of plots of scenarios of likelihood of consequences that are tuned with the owners, in which, let's say here we have an example of this demo 3 airports, Sadar Airport, that provides information, in this case unstructured via images, and with this information organized along the life cycle, asset information, monitoring, data collection, user requirements on the left part, throughout the whole life cycle, generating ways of assessing what is happening with the asset in, let's say, bespoke shape, bespoke or tailor-made way of seeing the information. We have tried to do it in a way that is user-friendly for the end user. And finally, the fourth step is the spatial geolocation. Okay, this is one of the tools called GC, which enables the connection between not only one asset but many assets, or in this case, not only this specific slide relates to one asset that covers large area, so every little part of the asset is also geolocated. This is one asset, or many assets covering larger areas that correspond to a territory. Okay, so this would be the fourth step. So with that, this is the overview presentation of what has been the maintenance phase within the ASHVIN project. Thank you very much for your attention. We will come back later.
Brilliant. Thank you, Rolando. So now we will have a deep dive to the ASHVIN demonstration sites. And we will start with the demonstration site focused on developing the digital technologies and validating it in airport infrastructure. And this specific demo site was managed by Irina Stepanovic from Infraplan Consulting, with the support from Ilias Koulalis from the Center for Research and Technology from Hellas. And they both will explain you a bit better their research and the work that they have conducted at this demo site. So I pass the floor to you, Irina and Ilias. Thank you.
Thank you very much, Mona. So as already introduced by Rolando and Mona, we will talk about the solutions for managing airport infrastructure, but of course it's applicable to other types of infrastructure as well. We'll give you a short introduction to the demo project, number 3 in our case, and it's airport infrastructure of Zadar Airport in Croatia. Then we'll present you the methodology, how to introduce drone images into the risk-based decision-making, and we will present you more in detail a damage detection model and demonstration of the tools. Nowadays, our transport infrastructure are exposed to a number of challenges, and we can say 3 most important, I would say, it's increased number of population or of the users, the climate change impacts which are causing a number of extreme weather events, and then also increase pollution, and in that sense we have to satisfy sustainability requirements, and all that with budget constraints. So how can we solve that? We'll try to show you a bit later. So our demo project is Zadar Airport, which is located in Croatia at the Adriatic coast, with a relatively small airport terminal and infrastructure with the plans to expand, but with the exponential increase of the users in the tourism season. So Zadar Airport was built 40 years ago, and this is the 2 runways. So this is shared with the military runway, and this is the runway which we are focusing on, which also increased the usage due to the increased traffic. The airport was partially renovated in 2016, and the goal was really to automate the process of damage detection with the usage of drones. 2 main problems I tried to explain also why and how we focused on these 2 types of damages on the runway itself. There are 2 main concerns regarding the airport, and these are related to the safety hazards caused by foreign object debris. Here you have an example of objects which are found or have been found on the airport runway. And unfortunately, they can cause serious damage. One of the most famous one is the crash of Concorde in 2000 in Charles de Gaulle Airport, which was actually caused by the small piece of titanium debris from the plane before, which was took off 4 minutes before the Concorde. The debris which we focused on, let's say, are the aggregate debris caused by the cracking of the runway. And the other big safety hazard may be caused by the decrease of the friction, especially in the wet weather conditions, and they often cause the aircraft excursion. So in that sense, why we focused on those 2 damages, or what we could detect by drone images, because we are talking explicitly about the 2D images taken from the distance. So we have focused on the detection of the cracks, joints, construction joints, and repaired cracks, which are, as you can see, also as they age, they also are a source of new cracks. And we focused on the tire marks. We have applied the ASTM method for payment condition index assessment, and of course, let's say adapted or simplified ASTM method. The other focus was, as I mentioned, on the detection of the tire marks percentage on the surface area. Regular or standardized test is tested by the cars, which is testing the friction coefficient. Based on our empirical data from one of our airports, we have developed a curve, which is correlation between the friction coefficient and the tire marks percentage. And in that sense, of course, we will populate this correlation as we get more data. But the idea is, of course, with the image processing that we can determine the moment when the friction will be decreased and potentially present a hazard risk. And we have to, of course, remove the rubber layers from the surface. What you can see here, so this is the looking for my mouse. This is the image of or video from the drone. So based on our images from the drone, which were taken with the high resolution camera, with the resolution 3 millimeters, so 1 pixel was a 3 millimeters, we were able to detect cracks, joints, construction joints, and tire marks. With the damage detection model, which Ilias will explain much more in detail, we classified and geolocated the damages, and then based on the quantity of the damages and thresholds applied from those standards, we have classified the runway as a condition assessment in this moment of time. So I give word to Ilias now.
Hello, everyone. Thank you, Irina. Well, I'm Ilias Koulalis. I'm representing CER, the Center for Research and Technology, and our role in ASHVIN involves deploying digital methods related to data fusion and computer vision tasks, which in turn are used to enhance the capabilities of the tools designed by ASHVIN. In this particular demo case, as mentioned, we have designed a damage detection method based on computer vision, fully capable to autonomously inspect visual content from drones and consistently detect a specific type of damages on runways. To achieve this, we've developed a method based on deep learning, the strength of which lies in the ability to learn and improve through training on comprehensive datasets. The first key element of our method is to enable automated visual detections of damages. And the second key element is to accurately identify and locate these damages using semantic segmentation. Next, please. But why semantic segmentation? Actually, semantic segmentation is a technique that involves labeling each pixel in an image functioning as a pixel level classification task. In classical object detection tasks, as shown on the top right, the model identifies bounding boxes around each individual detected class, resulting in a rough localization of the detected object within the image. Semantic segmentation takes this a step further by assigning a specific label to each individual pixel. This level of precision is very valuable for our application, where the goal is not only to identify the damage, but also to locate and detail and give back detailed information about the location, the exact shape and size of the damage. The architecture we employ for our task is UNet, which was originally designed for biomedical image segmentation, and it is called UNet due to its shape. UNet is a deep network composed architecture composed by various layers, each performing a unique function. In the lower layers, the model manages to identify low-level features such as simple pattern, edges, colors. And as we move higher, these basic patterns get combined with others to more complex representations that include objects and various attributes, as for example, in the given example, the distance between the ears of the cats, the mouth, the shape of the mouth, the size of the eyes, etc. Next, please. one key aspect of our work involves the creation of a custom-made dataset, which is a crucial element in training our network. The collection of the data was conducted by several drone flights, enabling us to capture a broad number of damage conditions. And this data was next annotated by infraplan and field experts to assigning labels to the pixels, including damages, adding a layer of semantic information to the raw data. The classes included in the annotation, as mentioned before, are joints, construction joints, cracks, and tire marks. Each of those corresponds to a specific type of damage that our model needs to identify. Our custom-made dataset currently features over 300 labeled images, and our aim is to continuously expand with new data to further improve the performance of the model. And now we would like to demonstrate with a video how our method functions in a real-world scenario. First, the collected data of drone inspection create an overview of the runway by J-reference tiles, each of those serving as a distinctive unit for damage inspection. And these tiles are fed one by one to our damage detection service, which use our trained deep network to identify damages and return a masked output. This mask is in pixel form, which have the specific color representation for each damage class. But in order this information to be usable, we further automatically process the output to extract the contours, and then the polygons describe these damages, and the extracted shapes are saved in shape files in JSON format. The coordinates of the polygons are then translated into real-world coordinates, creating GeoJSONs that can be easily used for mapping the damages in real maps, as it will be seen later. So by that, we end up with a functional method that can be used to monitor runaways in real-world scenarios and effectively be used as an element by the GC and the RISA tool, as it will be explained by Irina in the following for risk assessment. Thank you.
Thank you, Elias. Okay, so here you can see actually the whole methodology. So we are somewhere here, let's say. So we have drone images, we have damage detection, they are geolocated, and then we classify them in the same in the sense of payments. We say we get the payment condition index or we get the tire mark C index. Similar could be done for the bridges, and we could get the bridge condition index. And now we have to predict how those damages will evolve in the future. So we have a deterioration curves based on the loading or the different traffic scenarios in the case of airports, based on the local extreme events or climate conditions. For different deterioration or damage thresholds, we develop maintenance scenarios, also in collaboration with the infrastructure managers, which are mostly considering 4 options. So do nothing and monitor, minor repair, major repair, and replacement. Based on different maintenance scenarios, we develop life cycle cost methods for the service life as required by the owner or the manager. And then we develop risk scenarios. That means that for the option when I'm implementing a maintenance option, I'm decreasing the risk and potential consequences. But when I'm postponing the maintenance option, there are potential hazards which could happen, or there is a risk which might be acceptable or not acceptable. We can present the results in different ways and in the KPIs, which we try to integrate into the whole procedure. The concept of risk is that we define the failure mode. We determine the probability of failure of that failure mode over the time and over the different loading scenarios, and then the consequences of that particular failure. In our case, so we try to quantify the direct consequences and indirect consequences. So direct consequence is the maintenance cost or material damage on the infrastructure itself, and indirect costs are related to the operational delays of the airport in the case of, for instance, aircraft excursion, or in the case of FOD damage to the aircraft. So we use the statistical data for determining these average values for the operational delays of the airport caused by different accidents, and overall for the repair or unavailability of the airport to perform certain repair. So I will show you now the video as at the beginning Rahul presented. We are integrating our demo projects into ASHVIN platform. ASHVIN platform has the aim to present in a simple way all KPIs from the beginning, so from either from the birth of the structure or from the moment when we assessed this particular infrastructure, and then over time, integrating digital information collected by different sensors or by different monitoring techniques. In our case, those, as you know, those are drone images. So you can see here we have a BIM model of the runway. We have integrated the results of the damage detection tool with 4 categories of damages: tire marks, cracks, joints, and the construction joints. Runway is divided into 240 tiles, and we can by click we can upload the image of that particular one tile. And then the next is that we want to load timeline scenarios. So this is now the condition assessment at the end of 2022. And we are predicting now different development of those damages over time by actually integrating 2 maintenance scenarios. So first scenario is avoiding the risk and keeping the performance level always at in this green area. So whenever the threshold for the PCI has reached 85%, there is a minor repair applied. The other scenario is the opposite. So we postpone the maintenance activity as long as it goes to, which means we reach the end of the orange category, or 55% of the damage, and then we apply the maintenance. What we wanted to show that in one scenario the cost is smaller, but the risk is over the whole period very high. So we performed this prediction for 30 years. And in the other scenario, you invest over the time continuously a smaller amount of money, but you decrease the risk. So what we believe that this process of digitalization is enabling optimization, and it will reduce the costs and environmental impacts. In this particular case, also, if the drone would be implemented into infrastructure inspection in a daily routine, it would reduce significantly the impacts of the diesel vehicles usually applied at the airports. We can track damages over time. And in that sense, we can develop a performance model specific for that particular structure. We can, of course, extend these models to other types of damages and other applications. And the RISA model, which I have presented you here, enables infrastructure managers to develop different scenarios and compare different approaches. I want to acknowledge specifically this other airport management team and the great collaboration. And we also collaborate with Belgrade Airport and Zagreb Airport, who have provided us significant inputs for development of our models. So thank you very much for your attention.
Thank you, Irina, for sharing these really good results from Croatia. And now I will pass the floor back to Rolando from the Political University of Catalonia, who is managing 2 different demo sites in Spain related to bridge maintenance. So please go ahead, Rolando. And please be mindful of time so that we have the question and answer session in the end.
Thank you, Mona. Yeah, so let's now move to Spain and to the realm of bridges. Okay, we begin this presentation with demo number 1, which is high-speed railway network bridges in Spain. Okay, you can see here the map of Spain, in which there is a yellow line with the newly built high-speed railways network between Madrid and the Portuguese border. Okay, in this specific network, there is a segment in which a set of bridges were tested before going into the service. Okay, these 2 towns called Plasencia and Cáceres, and in this segment, 5 bridges were open to collaboration to Ashwin. Okay, these 5 bridges belong to the segment, as I mentioned, and this collaboration was performed with the company GeoCisa, which is now called Drace, and the owner of the system, which is the Spanish public company ADIF. Okay, so we have bridges from different kinds belonging to this network. So here we have a picture of the bridges. Simply supported 8-span bridge Valdelinares, a culvert, an underpass, a continuous beam, 4 spans, La Plata, and then a couple of arches that also, in which we were also assisting a little bit to what was happening. El Tajo and Almonte, 2 icons of Spanish engineering. So GeoCisa was performing routine load tests on those assets in that segment, measuring and reporting about the behavior of those tests. And our role there was to, on top of this layer, to try to create a digital birth of those assets at the same time as the routine load tests were being performed. Okay, here we have the team. I acknowledge the collaboration with the company. This is May 2021, 2 years ago. And so routine load tests, there are several steps in those, let's say, routine activities. First of all is to develop a set of simulations that predict the response of the assets under certain scenarios. Then to deploy the load tests themselves, and then measure key magnitudes, deflection, strains, and accelerations, and then comparing those key values between models and measurements to see how it is behaving, which helps assessing the basic structural behavior of the asset. Okay? Then everything is reported according to, in this case, Spanish standard, but in general, many countries have their standard on this report. So to deploy load tests, there is a big investment already. Big investment in logistics, in staff, in measurements, and then once it is done, everything is, say, okay with the bridge, then it goes to the service stage operation. But if we recall what we have been talking about the coexistence of many different sources of information, we have measurements, we have simulation, we have assessment, and we can have also integration. And if we see the routine load test, many of those sources of information are covered in the routine load test already, okay? But they are not encompassed in a single asset. So the idea was, okay, let's do that, let's perform those actions in a way that we can also create the virtual representation of the asset, not only reporting according to standards, but also digitally sound, okay? So here we can see, let's say, the preliminary sets of simulations that are quite standard from the structural perspective under certain scenarios. Here we have the scenarios with the locomotives applied and as loads in a way that we see also with the abstract representation of those beams, as structural engineers do. As we measured together with collaborators, or we collaborate in those measurements, both to the static measurements and the dynamic measurements, which are routine as well. Information was primarily time strings, primarily with sensors. That was the sources of information, with strains, with deflections, and with acceleration. Okay, that was then sent to the IoT platform. But also, after the numerical simulations were embedded into the digital twin platform in a way that they were not only those preliminary responses, but also more sophisticated responses to validate those models that were embedded into the digital twin platform, in this case for the La Plata Bridge, which represents a complex section with voids, and so we used, in this case, fiber-based BIM models. Information was, from our side, not only measured using time streams, but also we added some other layers like photogrammetry in some of the assets, in this case, the culvert, underpass, with videos and images. We reproduced the geometry of this asset. So that's another way of putting together information that can be part of this virtual representation. Or also we were we also assisted to the use of remote sensing techniques in the biggest assets, in this case, credit to GeoZone, a company that provided service to this specific use of remote sensing techniques, which is INSAR radar. Due to the size of the asset, it was not possible to use regular sensors, standard sensor, but other type of measurements. So assessment standard, according to the standard Spanish guidelines of routine load test. So comparing key values, that is now under development, under implementation in the digital twin platform to just visualize how it is. Okay, so as a result, we have that the physical asset and the reporting that is routine is now also including a virtual representation of the load test in order to be used in the future when this specific asset is under maintenance or under scrutiny, when time elapses and things evolve. Okay, so that's the main idea. Also, it is possible to integrate those assets in the network, okay, which represents another added value. Let's now move to demo 7, Road Bridge, Barcelona area. Okay, this is a bridge, a single asset, one of them, which is under service already. 2 years ago it opened. So this is it joins 2 main highways in Barcelona area. This asset is a composite bridge, steel plated, longitudinally stiffened, transversely stiffened, and also there is a concrete slab on the top. Okay, it is more than 800 meters long bridge. Okay. And again, here the idea was to encompass in a common data environment, which is digital twin, measurement, simulations, analysis for helping to this decision making. Okay, so the idea here is, let's measure as many things as possible. Let's simulate as many things as possible. And measurement, simulation, analysis is then giving us information in the form of a performance indicator. For each measurement, there should be at the end of the information pipeline. Now I put this name here, information pipeline from measurement to the performance indicator. So there are several. There can be several. And the maintenance plan should be the result of the aggregation of all these performance indicators in this decision-making process with information behind. Okay. First of all, we needed to transform the existing data from the bridge into some useful data geometrical model. Okay, IFC in this case, IFC model. When I mean useful, I'm referring to that this is a 3D comprehensive metadata rich model that is then added with other sources of information. Okay, and for the measurements here, we try to be comprehensive, including sensors, including images, and including remote sensing techniques. Okay, but today I will only focus on one of them, terrestrial laser scanner remote sensing techniques, because with that one, we could try to understand the seasonal behavior of the bridge, which may be one interesting measurement that is forming the set of different performance indicators of it. Okay, so we measured a specific portion of the bridge that is can see in the slide, not the whole 800 meters, but only a target bridge section, okay, with a laser scanner. This was performed seasonally, okay, during a year in several seasons. There were no really extreme difference between temperatures or conditions, since we are in a mild Mediterranean area, in which the difference is not that extreme as in other cases in Europe, of course. But in any case, we have this a little bit more than a year seasonal measurements. The result of it is a point cloud unstructured that needed to be then segmented and identified to be useful. Okay, as we can see here, it goes from B to A in this case, from B to A, from the unstructured to something structured. And with that, once identified every little panel of the portion that was measured, we could track, you can see here M1, M2, M3, and 4, which represent the actual shape of that specific plate of that bridge a long time. So those are the shapes. And the shapes then, on a routine basis, can be used for developing complex numerical simulations, either for single panels or for partial web, for full webs, or even for a full section. For the moment, we cannot say we have this in a way that we have the whole bridge. This is a lot of information. We cannot deal with this information today, but full sections and full portions, that's possible, okay? And with that, the idea is, or has been, to reproduce the structural behavior of the portions that we are interested in understanding, and then use this information for this analysis. Okay, so this should give a performance indicator for the whole bridge. And then with other measurements, other performance indicators, and the maintenance plan can be based on aggregation of those elements and to be more data informed. Okay, so to finish here, we have on the right, let's say, the potential stakeholders in a maintenance plan decision making process, in which there are, let's say, visual inspections or measurements sent to the IoT platform that are there. Then stakeholders can visualize information in the digital twin platform, and in this digital twin platform, with these performance indicators assessed, they can either request back simulations or visual inspections to then continue with the process, with the loop, and eventually become or perform this decision making in a more informed way. Okay, so that is my part for the demos in Spain. I hope it is clearer now, and thank you very much for your attention.
Brilliant, thank you. Thanks a lot, Rolando. So what I propose is that all our speakers put their camera on, and now we will pass to the more interactive part of the session for the last remaining minutes. So you can either draft your question on the chat, and we can pick up from there, or you can raise your hand, and I can then pass the floor to persons who would like to ask something from our speakers. But otherwise, so let's start. So if there is any questions, please raise your hand and I will give the floor to you. Otherwise, we can also have a little dialogue in between our speakers. So I cannot see any hands raised for the moment. Don't be shy. You have been good listeners until now. So maybe, Irina, you have prepared something you wanted to share a bit outside.
I would like, so I can ask Rolando, because we did a little bit different project. So Rolando, you did a digital twin of the load test of the bridge. Could you maybe explain what's your assessment, for instance, of the increase of the costs by including development of digital twin? And how would you see the implementation of this in the future bridge management system?
Yeah, well, I think that the cost of a load test today is related to perhaps the same things that we have done when it comes to creating the virtual representation. I mean, the biggest cost is related to the logistics and the staff involved and going there and measuring there, which will happen for the routine or for the virtual representation creation as well, meaning that's the same cost. So on top of the engineering hours that are needed for that, of course, this was a first step, which may have taken longer hours than the next one, of course. But I would say that the increment of cost is not greater than 15% or 20% of the actual cost.
Yeah, and then I guess there is a benefit which is even hard to explain.
Yeah.
For
The benefit is
life cycle management is that you're aware of and you can plan and know whatever, if anything is happening, which is let's say out of that what we were expecting, you can always compare to the initial load test and the response of the structure.
Exactly, that's done. You don't have to go back to documents or PDF to check things manually, but there is something that can be even improved in the future.
Maybe Rahul, it's good. I think people are very impressed by our ASHVIN platform.
Yeah, you can decrease the cost of load now, not at the moment what for first stage with the Rolando has done, but now when you have a virtual model of a bridge, you can put the virtual model of a train or a virtual model of a truck if it's a road bridge, and then you can test those scenarios. So you do not have to send all the time the trains for the loads testing. You can do this virtually also with the proper physics model of a train, and then you can get a simulation result from the platform, and this will reduce your cost for the testing in future drastically.
Yeah, exactly. I wanted to say, I mean, the value of the digital twin is, I think we cannot even predict what are all the benefits we will.
The value of the digital twin comes once we have a proper, not the digital model, but the physical model, physics model, not the physical, but the physics model. When we have each and of every asset of a physics model we have in a virtual reality or virtual this system, and then the cost will reduce drastically because people can plan, people can be much better doing the testing on or not using the physical model or physical thing, and that reduce the cost. Also going towards to the bridges, and every time they can do sitting in their office, or these days everyone is doing home office, so home. Yeah, that can reduce quite a much one. The whole process of the digital twin is not to create just a digital model. It is about create a physics model of each and every asset, and then it will replicate a quite huge amount of cost from the construction site.
Perfect. We do have a question from a participant that I'm just now writing on the chat. So if you can maybe read it, Rahul, and then we will see who can reply.
Okay, so did the graphic BIM model made manually, or did you develop or use automatic or semi-automatic techniques to create the models? And did you use semantically enrichment by software or manually? So, Rolando?
Yeah, this question has many answers since we have 10 demo sites, so 10 answers.
Just to make one
yes.
yeah, just
but,
to make one answer.
Well, in the case of demo 7, which was very rich in different specific structural elements, it was done manually, but let's say using the force of programming, of course. It's a little bit difficult to say, but it's using Grasshopper, programming systematically parametric model, but many things were manual because the PDF were we needed to read that and so forth. But on the other case, the demo site number 1 was the PDF that we got from source information were relatively rich with layers, and then it was easier in that case. So it depends a little bit on the source of information. It may be very manual or not necessarily.
Surely, at this moment, when we are talking about the infrastructure maintenance, even in Europe, even the best country out in Europe, also we do not have a digital model of those infrastructure. We have AutoCAD files in a PDF format or other formats to convert into BIM. So first of all, to convert this into 3D model, that's the first step, and then to add the parameters, what Rolando just mentioned. So at this moment in ASHVIN project, we have done manually and many of the things. Further simulations will be done automatically there, but creation of the BIM model was for these infrastructure was manually. From one of the recent application, I would like to mention here from the Rhino company. They have created the iRhino app, but it is unfortunately available only for the iOS, and that's really interesting. You can scan your AutoCAD file, you can create your own 3D model also. So that will reduce quite a much time for manual work to create your BIM model. So I would suggest to use those. It's free to use by anyone to download on the iOS application.
Perfect. Thank you, Rahul. So we are running out of time, but I would propose to have a last question from Michael Holmes. So Michael, please go and unmute yourself and ask the question, and that would be perfect.
Yeah, I just want to ask you guys, how do you accurately measure anything in the real world, and how do you verify those measurements?
So accurate measurement. Okay, so that's the measurement has been done like using the LiDAR scanners provided by Leica system or Faro system. So those things, first of all, to measure those, to validate this thing, whether we have measured correctly or not. So this is two things. It's not that one thing is if the infrastructure is small, then we can measure it by ourselves that it has been validated, for example. But mostly we depend on the accuracy of these devices. So there are LiDAR scanners provided by many companies with different accuracy. So the system which has been used by Rolando on the site is by the Faro system, has a very good accuracy from the civil engineering point of view. So that is how we validate that the measurement has been done.
If I may add a little bit, it's well, demo one was actually one attempt of using the very precise measurements collected for the routine load test, which is, of course, still there is an accuracy. There is no like perfection, but it was very high. To then grasp this information to validate models. So that was perfect as an academic way of having like a lab for us, which was great.
Right. So this Faro system gives the accuracy in between 1 to 3 millimeters. So it can give you that much of accuracy. 100% accuracy, I do not think so at the moment any system can provide, but 1 to 3 mm still it's good enough than nothing.
And that allows you to record motion over time at a reasonable frequency.
Yes.
Because if a train is driving over a bridge, you need to sample that 100 times a second or something, right? To have anything useful. And you can do that with these because they
movement of the train we do not record with a laser scan or LiDAR scan. Movement of the train, there are sensors installed, and then we collect that information. So movement of the train is not based. In the video which you have seen, the train is moving, or the model of the train is moving. That's not basically we recorded that part. It is just with the sensor and the time we are moving it further.
And what sensors?
It was LVDTs and strain gauges. Yeah.
Oh, right. Okay, thank you.
Brilliant. Thank you all so much. Thank you for our participants for your time and interest in ASHVIN. We will keep you in the loop for forthcoming webinars about our research and results. Thank you for our 4 speakers for your really good insights in your work. And we will conclude by saying that the recording will be available online on our account. And I will also ask the participants to fill in a short stakeholder survey to share us your feedback on the research that we have presented and the session. So with this, I would really like to thank you one more time and wish you a really good afternoon. And now I will close the session. Thank you so much for everybody. Bye-bye.
Thank you, everyone.
Thank you, everyone.